Welcome, everyone. Today, we are going to demystify reinforcement learning for model training. We will build up from first principles, stripping away the heavy optimal control theory jargon to focus purely on the intuition behind training large language models. Finally, we will explore some exciting future directions, including a new framework called GRAPE. Let's dive in. Let's start with the shift from completion to instruction. Pre-training is essentially an autocomplete engine. It recursively predicts the next likely token based on a massive corpus of data. But to make models truly useful, we need them to follow instructions and answer questions. We achieve this through instruction tuning, which constrains the model's distribution. By using specific delimiter tokens, like user and model, we condition the model to trigger an answer mode. Mathematically, however, it remains a next token prediction task. So, how does the math actually work for this? This brings us to the first principles of Supervised Fine-Tuning, or SFT. SFT forces the model to mimic high-quality training data. The loss function here is all about minimizing the negative log likelihood, which is exactly the same as maximizing the likelihood. Simply put, if the model assigns a high probability to the correct ground truth token based on the previous context, the loss is low. Once we have an instruction-tuned model, we want to scale our training. The first step toward learning preferences is rejection sampling. We give the model a prompt, generate multiple samples at a high temperature, rank them, and pick the winner to use as SFT training data. But this has major flaws. It learns discretely in steps, lacks a negative signal to tell the model what not to do, is computationally wasteful, and carries a high risk of model collapse due to reward hacking. To fix the flaws of rejection sampling, we introduce the reward signal through an algorithm called reinforce. Instead of discarding all the losing samples, we weigh the gradient update by how good the sample actually is. We use an advantage function, which compares the actual reward of a text to a baseline, often calculated by a separate critic model. If the advantage is positive, we push the probability of those tokens up. If it's negative, we push it down. But reinforce introduces a stability crisis. Updating a model changes its distribution, and if we update too fast, the model forgets its pre-training and collapses. Enter Trust Region Policy Optimization, or TRPO. TRPO solves this by introducing a KL divergence constraint. Think of KL divergence as a spring measuring the distance between the old policy and the new policy. TRPO uses this distance as a hard constraint to prevent destructive, radical updates. TRPO is mathematically complex, which led to Proximal Policy Optimization, or PPO, the current industry standard. PPO simplifies TRPO using a technique called clipping. The intuition is brilliant. If the new model becomes vastly more probable than the old model, exceeding a ratio of 1 plus epsilon, we simply stop rewarding it. This zero gradient ceiling prevents the model from changing too radically and falling off a cliff. PPO is great, but it requires a separate value model, or critic, to estimate the baseline, which doubles your memory usage. Group Relative Policy Optimization, or GRPO, famously used by models like DeepSeek, removes the critic entirely. The solution? Generate a group of responses and use the average reward of that specific group as the baseline. This results in significant compute savings since no separate critic model is needed. Can we simplify even further? Direct Preference Optimization, or DPO, removes the reward model. The core question DPO asks is, why train a separate reward model to train a policy, when the policy can be the reward model? DPO derives the loss directly from preference data, comparing a winning response versus a losing one, implicitly handling the KL constraint without needing an explicit reward loop. Despite these advances, we are hitting the limits of outcome supervision. The bottlenecks are clear. Human labelers are slow and expensive, and simple right or wrong outcome labels aren't granular enough for complex reasoning. The emerging solutions to this are RLAIF, using AI to give feedback, process supervision, which rewards the steps of reasoning instead of just the final answer, and game theory setups like debates and self-play. This brings us to a new framework, Generalized Relative Advantage Policy Evolution, or GRAPE. GRAPE is a unified framework that replaces the opaque, black box reward model with specific, category-based rubrics and system prompts. Instead of getting a single arbitrary score, the GRAPE way generates an itemized critique checking for explicit things like safety, math correctness, and code efficiency. Let's look at the mechanics of GRAPE. For every rubric item, the scoring model outputs three things: reasoning for why it's good or bad, a score from 0 to 1, and crucially, a confidence level. Why include confidence? Because low confidence usually indicates a poorly written rubric item. By weighting the final score by the model's confidence, we create an automatic noise filter that improves the reliability of the reward. In practice, the GRAPE workflow operates in a continuous 4-step cycle. Step 1. Categorize the prompt into domains like math, code, or safety. Step 2. Apply the rubric, using atomization to break vague goals into concrete checks. Step 3. Critique and score the response to generate the reasoning, score, and confidence. Finally, Step 4. Update the policy by calculating the advantage and taking a step. To summarize the evolution of optimization, SFT gives us base capability at a low compute cost. PPO is the stable industry standard but comes with high compute cost and complexity. DPO offers medium complexity with a low cost by eliminating the reward model. GRPO brings medium compute cost and complexity by using a group relative advantage. Finally, GRAPE offers high flexibility and granularity by being a fully rubric-based, self-correcting system. Looking ahead, the future of alignment isn't just about human labels. It is about self-referential, granular, and confidence-weighted evolution. As we shift toward reasoning and process supervision, we are seeing the historical trade-off between safety and capability begin to converge. By teaching models to reason better step by step, we inherently make them safer and more capable simultaneously. Thank you for watching.